law of studying thermodynamics. Thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you know you don't understand it, but by that time you're so used to it, it doesn't bother you anymore. Attributed to Arnold Sommerfeld. I really like that. Having taught thermodynamics for quite a while now, there are still points I have questions about. There are still things I don't understand. There are still things I'd like to look into, and I learn something new every time I teach the class. Try to expand what I do in the class a little bit every semester as well. But there's a lot of truth to this. One of the reasons that thermodynamics seems difficult is because there's so many things that go into it. There's so many things you have to know. But first of all, what is thermodynamics? Well, it's just basically heat power. It's really the conversion of thermal energy, which in common language is usually called heat, though the heat's a little different in our vocabulary. And it's conversion to work. And energy conversion in general is the main thing we're interested in thermodynamics. Now, I've tried to sell this to you before, probably telling you that thermodynamics is all about race cars and cold beer. And in a way, that's actually true, because the conversion of thermal energy into work is a big part of thermodynamics. Now, race cars is one place where that happens, unless you're talking about an electric race car. In that case, there's still energy conversion from chemical energy, but more directly into mechanical energy or into kinetic energy. But a lot of times, race cars use engines that burn a fuel, whether it be, methanol or gasoline or whatever the case may be. But these engines take chemical energy and first convert it into thermal energy, what you would have called heat before this class, and then convert that thermal energy into work, pushing the car down the road, hopefully winning the race. On the other hand, removing excess thermal energy from food so that it can be kept cold and taste better and not go bad so quickly is another huge area of application for thermodynamics. So this topic is very, very important to most of our modern world. And I think it's kind of a tragedy that fewer people actually study it and understand it to any extent, because it's really it's such a cornerstone to our modern society. In any case, it's perceived as a difficult topic, and at first, there can be a lot of new stuff, a lot of new variables, nomenclature. We have to deal with a little bit of chemistry, the behavior of fluids, and you have to use units. But to be fair, in any endeavor you undertake, if you're not using units with numbers, what are you doing? You're not representing reality, right? I mean, maybe you're a pure mathematician, okay? If that's the case, then maybe pure numbers are interesting to you. But most of the time, especially in engineering, we have to use units. It doesn't matter what sub-part of the discipline you're talking about. Units are critical. I was just talking to my daughter. She's in 6th grade, and she's trying to figure out how to do the algebra-ish sort of equations they're giving her and word problems. And I'm trying to convince her to use units, even though, of course, they're not teaching that in school. I wish they did. But I'm trying to show her how units can really aid you quite a lot. It can help you avoid making mistakes. It can help guide you in your problem. And, it's just something that you have to do as an engineer. You don't have any choice. I tried to illustrate it with her today. I said, what if I told you I'm going to give you 3? 3 what, right? Are we talking about 3 punishments? Are we talking about $3? Is it 3 pieces of candy? The units make a difference, right? What is this thing that is a quantity of 3? That's really important to her, obviously, right? So using units in everything we do is very important. So if you say, the answer to the problem's 3, it doesn't tell me anything. I need to know, are you talking about 3 feet, 3 joules, 3 BTUs? What do you mean this is the answer? Now, there are some things that are dimensionless or non-dimensional, and those numbers can be very important. However, those numbers are always still a ratio of 2 physical things, 2 things that are real things, where the units cancel. Each one of those items most often have units. Now, you can take ratios of dimensionless numbers, but that's not something we're going to talk about in this class. So, from your perspective, you need to get used to using units, whether you like them or not. So I had a student who took a test, and they knew that I wanted them to calculate work. They knew that work is force times distance, so they multiplied the closest thing they saw in the problem statement that kind of looked like force, 150 kilopascals, and multiplied it by a difference in distance. I had given two distances, they took the difference, and came out with units of kilonewtons per meter. Well, the only problem with that is those are not valid units of work. Work has units of energy, or dimension of energy. So something like force times distance would be like newtons times meters, or kilonewtons times meters. That's what the student should have expected. And so they gave me an answer. I don't even remember the number. I think these are the correct numbers that I gave them and what they used, but they were just trying to grab things and mash them together, and it just doesn't work. You have to understand that every equation you deal with has terms in it, and every one of those terms means something physically, and you've got to know what those things are. And that's, to me, the hardest part of thermodynamics. Because these equations we're dealing with relate real things to one another, and it's important to know what those real things are. So 150 kilopascals, I can tell you, is either a pressure or a stress. In this context, it was probably a pressure. I don't remember right now. Meters were a distance. There were a couple of distances something moved through. Well, what the student should have used was the equation for boundary work. And often I hear students tell me, you know, the problem on the exam was I didn't know what equation to use. I didn't know what formula to take all those numbers and just plug them into. Well, if you didn't know what equation to use, you haven't learned the curriculum and the material to the level that you should have. You should understand each equation as we go through it. I will describe what the equation is. I'll tell you what the elements are, the variables that go into that equation, what they mean. You've got to somehow learn those things and keep them straight. Otherwise, you won't know what equation to use because you'll have no idea how these things are related to one another. There are some very basic principles that we apply in this class. Number one is an energy balance, where energy is conserved. That is a basic principle, but you have to know all the different forms that energy can take on and how they can be transformed from one to another. Of course, that's something you learn as we go along. So try to pay attention not just to, oh, here's another equation. Pay attention to, when can I use this equation? What do the things mean that are in it physically? What do they represent in the real world? And of course, you've got to realize that these equations are not perfect. You know, I love Mythbusters, and Mythbusters often does some calculations and some predictions based on math. They don't show you the math typically, but the real world is often much more complicated than this theoretical world, this calculation world that we create using equations. Now, I'm not saying that energy conservation is not quite right. Obviously, if there are nuclear reactions, then, you know, energy can be transformed from mass. Mass can be converted into energy, but that's not what we're talking about in this class. So energy, technically, yes, it is conserved. There's a lot of things in science built on that idea, and if we find that energy is not conserved, there's a lot of things that are going to fall flat on their face. It's just, I don't think that's going to happen. We've come too far, and it's such a good model, it works so well, that I really do think energy is conserved. I don't think you're going to make it out of nothing. If you could, I think it's going to be destroyed pretty quickly. I think that in, you know, average energy is going to be conserved, and I think strictly speaking it's completely conserved. But I haven't been to every corner of every universe in existence, so, you know, I like to take I like to use what I learn effectively because it works, but I'm not so arrogant as to say I know everything about, you know, everything that exists. Anyway, in this case, the student should have used the boundary work equation, which talks about how, as pressure changes and volume of a container changes, work can be done, or work can be done by the system or on the system. And so in this particular case, there's a particular integrated form of the boundary work equation the student should have used that includes pressure, and I've shown it there before, or below. So make sure you don't just go through and kind of half listen to what I have to say. Try to really take it in, and if you have to pause the videos and go back and study it, or read it in the textbook a little bit to get another perspective, be sure to do that, because you really need to understand everything in this course. Now, to prove that units can be beneficial to us, we could calculate the amount of time required for a race to be completed. Let's say we know the course length, we know average speed, we know how many laps the drivers have to take, and so forth. Well, we can carefully put these numbers together in such a way that their units come out with what we want, right? Our question is, how many hours per race? Well, per means over, right? So hours over race are the units that we want. So as long as we're careful and we put, how many miles there are per lap in, how many laps per race, and miles per hour in the correct places, the units will cancel nicely and we'll get hours per race. It turns out it's about an hour per race. What you'll notice, though, is that I worked with the units first, and that's something you should get in the habit of doing. I can't stress this enough. I've got, obviously I teach in technology, but I've helped a lot of engineering students in other programs that I know personally that have come to me with questions, and everyone has the same problem, and it is, actually using and applying units. They're actually really easy. They're just fractions, really. That's all they are. So they work just like any other number, that's strictly a numerical number would work. So these units are very easy. You can see one place here where in the second line, the first fraction there, miles per hour, is inverted and multiplied. You can do that. They're just a fraction. So don't be afraid of units. And please, if you plug a number into an equation, make sure you know what units go with it, or just don't, right? Stop, figure it out, because if you get stuck and you're, say, on an exam and you're not sure what to plug in, you're not going to get the right number. The chance of you getting the right number, even if you have the right approach, are relatively low. And I don't say that to discourage you, because the way I grade, I look at your approach. I look at, what did you understand about the physical principles? That's what I care about. I don't really care if you give me the right number or not. I care about your approach and your understanding of the topic. Because really what I'm trying to do here is sharpen your intuition, sharpen your understanding of the way the physical world really works. That to me is the value in all of this. Now be careful with units, because you can't just say, well, if I get the right units out for the thing I'm looking for, everything's all right. Let's talk about the area of a circle, for example. If you think about the units of area and you know the diameter of the circle, you might think, well, let's see, feet squared are area, so couldn't I just take the diameter and square it? Well, obviously not. That's the area of a square. The area of the circle has a multiplier on it, right? Pi over 4. That scales the d squared. Notice d squared is still in there, right? The area of the circle is pi over 4d squared. It's still in there, but it needs a scaling factor, a constant of pi over 4. So that pi over 4 is a geometry thing, right? It's something that takes into account the fact that this is a shape of a circle and not the shape of a square. But the diameter squared is still an important piece. By the way, if you try to take the natural logarithm of a number and that number has units associated with it, you've made a mistake. Now, I know I said that every number should have units. That's true, but in the argument for the natural log, or even in an exponent, typically what you've got are ratios where the units cancel out. Now there are some equations that involve natural logarithms and exponents that are curve fit equations, and you have to use the correct units for those curve fits, or the constants in the curve fit don't work. But we won't encounter that hardly at all in this class, if at all. We encounter that in other classes like machine elements, but typically not this class. So arguments that are like exponents or that go into the natural logarithm need to be non-dimensional numbers. Speaking of dimensions and units, what's the difference? I sometimes confuse the two, but honestly, there is a big difference between the two. Dimensions are things that exist, whether we give them a name and recognize them or not. For example, mass exists, length, time, temperature, force. All these things are just things that are there whether we know it or not. On the other hand, units are certain amounts of these things that we all agree on. For example, we all agree on how much is a kilogram of mass, or how long a foot is, or how much temperature change is a degree Fahrenheit, and so forth. Now, there are primary and secondary units to consider. And we could talk about primary and secondary dimensions too, because those exist. Mass, for example, can't be broken down into anything more simple. I mean, you can represent mass with other dimensions, things that are secondary dimensions, like force, for example, has mass built into it. But mass is a simpler thing than is force. So mass is a primary dimension because you can't represent mass any more simply than just mass. In the same way, length is a primary dimension. So is time, so is temperature. But force, as I said, is a secondary dimension because you can write it in terms of other dimensions that are more basic, more simple dimensions. As a matter of fact, force can be written as mass multiplied by acceleration. And you might look at this and say, well, acceleration, mass, that's force, okay. But I'd rather think of mass and acceleration because I'm comfortable with those rather than force. Well, force is in itself a valid dimension separate from mass and acceleration. We can just write force in terms of mass and acceleration, and you're probably comfortable with acceleration, but if you think about it, acceleration is a secondary dimension itself, right? Acceleration is length per time squared. So length is a primary dimension, time is a primary dimension. So acceleration can be written in terms of simpler primary dimensions. So it shouldn't really be an uncomfortable surprise that force can be written in terms of mass, length, and time, right? It's mass times, mass times length over time squared. Now, in the SI units system, this is pretty easy, right? A Newton is 1 kilogram times 1 meter per second squared. And a lot of you may have decided that you like the metric system a lot better than the English system, because after all, that's the system that engineers really use. And if you're a real engineer, you use metric. Well, not really. I like the fact that there is more than one system used in this country. It does lead to some problems, like spacecraft crashing on Mars, for example. Yeah, that's a problem. But I think that you're a better engineer once you understand that it really doesn't matter what unit you use. What you should be focusing on is understanding the dimensions themselves. But besides my opinion, both SI and English units are used commonly in the engineering world today. At least in the United States. So it's important that, since that's most likely where you're going to practice, it's important that you understand both systems. And I think you'll be a better engineer for it if you'll just do the work and understand. Don't be biased by, I have a metric set of sockets at home and I hate it when I encounter an English bolt or vice versa. Tools are just tools, right? In the same way, so are units. Units are just tools that we use so that we can figure things out, so that we can make things better. So in English, of course, there's this thing known as G sub c. I don't like it being given a name like that, because G sub c is really just a conversion factor. That's all it really is. Nothing more, nothing less. You might remember it as 32.2, but then you might be confused because 32.2 is the acceleration of gravity on Earth's surface roughly at 32.2 feet per second squared. And so you might say, well, I see feet per second squared in there, but they've thrown in pounds mass and pounds force. How did they do that? Well, it's just a conversion. Look at the SI units for just a moment. You've got mass, you've got acceleration multiplied by each other, and that yields force on the left. That's really all that we're doing with this thing called G sub c, except it's the ratio of those two. It's force over mass times acceleration. So if you look at the English equivalent to what I wrote in SI up there, we've got 1 pound force on the left-hand side, and on the right-hand side, we've got 32.2 pound mass foot per second squared. Now, I could have written the SI conversion, if you will, between force, mass, and acceleration. I could have written it in the same manner. I could have written 1 kilogram meter per second squared, where I put all of those units and just mashed them together. It would have been the same thing. Now, in SI, of course, 1 unit Newton is 1 kilogram meter per second squared, whereas in English units, 1 pound force is not 1 pound mass foot per second squared, and that's where students get confused. Now, they get confused because they don't think of force, I think, as a dimension like you would length. If you had a ruler sitting in front of you, the ruler, you could look at it and you would know that from 0 to 12 is 1 foot, and it's broken up into 12 parts. There's 12 inches there. And you're used to this. It's not something that surprises you anymore. And for me to say 1 foot equals 12 inches makes perfect sense. You probably wouldn't even have to think about that. But if I took off the units and said 1 equals 12, you might say, what? What do you mean? Right? So you can see the importance of units. But also, you're probably pretty comfortable with this idea that you can have different amounts of length. I mean, that's simple, right? An inch, a foot. No big deal. Well, force is the same way. It just so happens that in SI, by definition, 1 Newton, this much of it, is 1 kilogram meter per second squared. But in SI units, 1 pound force, let's see, how would I do that? Yeah, 1 pound force takes 32.2 little pound mass foot per second squared. So you should realize that the pound mass foot per second squared is more like an inch in that it takes more of them than just 1 to generate 1 pound force. So if I were to come up to you and I shove you with 20 pounds, you're probably going to go flying across the room. unless you were prepared and had yourself stabilized so that you didn't go flying. But if I came up to you and I pushed on you with 20 pound mass foot per second squared, you'd hardly feel it because it'd be about 1/32 of the 20 pounds force. So I hope that helps you understand. And I don't really like G sub c because students often think, well, do I need to multiply or divide by G sub c? I prefer looking at it as 1 pound force is 32.2 pound mass foot per second squared. The reason I like that is because I can think of it as force equals mass times acceleration. And I can remember 1 pound force, no problem, equals 1 pound mass on the right hand side times the easiest acceleration I remember is 32.2 feet per second squared. Put it all together and I've got the conversion factor. So that's just a little memory trick that I use for going back and forth between force and mass times acceleration in English units. Now, one important thing to be aware of is energy. And there's a lot of different forms of energy, and we got to keep track of all of them in this class. I often say that we are energy accountants. This really, instead of thermodynamics, we should call this class Energy Accounting 102 or 101 or whatever you want to call it. But there are some forms of energy that you're probably already familiar with and some that you may not be as familiar with. Potential energy, for example. If I asked you to write out an equation for potential energy, you'd write mgh, right? No problem. The mass times the height times the acceleration of gravity. Now understand, let's focus on this equation for a minute. This is an equation that quantifies the amount of potential energy in a body, and each one of the terms means something. The potential energy is obviously a secondary dimension, isn't it? Mass is primary, g being acceleration is secondary, it's length per time squared, and height then is a primary dimension of length. Now, what do these things represent physically? Well, m is the mass of the thing that has potential energy. G is the acceleration of gravity that that body happens to be experiencing, whether it's on Mars or the Earth or wherever it happens to be. H is the height that represents the potential, right? The amount that the body could fall. If I take a paperweight and I set it on my desk, its potential energy is exactly zero. It has no height that it can fall through. Now, if I raise it up to the ceiling, then whatever that height is how far that body could fall, right? And I've given the body then potential energy. It's important to understand on the left-hand side, potential energy is not just some vague concept. That's the potential energy the body literally possesses that it could potentially, use to do something. It could be used to accelerate the body, for example. So if the body's allowed to fall under the influence of gravity, then obviously that potential energy is going to be converted into something else, and you probably know that something else is kinetic energy. Now, the kinetic energy of, say, a car going down the road, or Wile E. Coyote just before he hits the ground, is 1/2 mv squared, where m is the mass of the body, again, just as it was before. But v now is the velocity of that body, okay? And then ke is the kinetic energy of that body. Now we can talk about the wheels on a car if we think about a more complicated system and we're looking in a little more detail at a little more accurate model of kinetic energy. As the car is going down the road, let's say it's not just falling off a cliff or something, as it's going down the road its wheels are spinning and therefore have kinetic energy. And we can quantify the kinetic energy of the wheels as 1/2 I omega squared, where I is the mass moment of inertia of that wheel and omega is the angular speed in radians per second. So all of these things can help us to quantify the amount of energy that bodies can possess, whether they are rotating, like the wheel, translating, like the car, or have the potential to fall, like poor Wile E. Coyote here again. By the way, what is a radian? We said radians per second. Most people really like degrees because they learn there are 360 degrees in a circle. They begin to memorize things like 90 degrees in a quarter circle and so forth. But what is a radian? Well, a radian is actually defined as the arc that's generated when, or the angle, I'm sorry, that's generated when an arc measures the same length as the radius, r. Now, if you think about this for a little while, you can figure out why that means that radians are dimensionless, in fact. But it turns out it's about 57.29, etc. degrees, if you're curious. So that's what a radian is. So if you grab your calculator and you take the ratio of 360 degrees to 57.29, you'd get 2 pi. So it would take 2 pi times 57.29, etc. to come up with the total 360 degrees of the whole circle. What about energy that you may not be as familiar with, but you probably experience every single day? Well, these are microscopic forms of energy, energy that you can't typically see, but that are in fact there. And you've sensed all of these. You probably realize that a can of gasoline has quite a bit of energy in it. Well, unfortunately, a lot of people try to say that gasoline has potential energy in it. Potential energy is something that I would rather leave to objects falling in a gravity field, or an object or a charge moving through an electrical field, because that's potential where the particle can be accelerated. In a sense, yes, the chemical energy in the gasoline allows that gasoline to be accelerated, but only when you burn it, right? I mean, when you burn gasoline, what happens is you're basically taking carbon and hydrogen, you're reacting it with oxygen to produce carbon dioxide and water. And so that's why when you drive down the road, there's actually water coming out of your tailpipe. You may not realize it, but of course when you stop and you shut off the engine and all the exhaust gases in the exhaust system just sit there and cool off, the water condenses out. That's how you get water inside of your muffler. And by the way, that's how your muffler often will rust from the inside out, because of the water that's there that helps catalyze the rusting reaction. But anyway, when you burn gasoline or diesel or wood for that matter, really what you're doing is burning primarily carbon and hydrogen bearing compounds that are converted into water and carbon dioxide, which have lower energies in their bonds, and so since energy is conserved, that energy has to be released somehow. Now, when you just burn a fuel like this, the energy turns into thermal energy. So that excess bond energy reappears as the molecules bouncing around. So in a sense, yes, it's potential because it's made the molecules move around on the molecular scale. But as I said, I would prefer to think of potential energy in the context of a field where linear acceleration of the bulk particle can occur. Chemical energy and thermal energy, I like to understand, I like to think of in a different way than potential energy. You could talk about thermal energy as potential energy if you really wanted to, because it has the potential to do some work. We'll learn that you can't take all the thermal energy, though, and convert it completely into work where the particles are just sitting still. That's not something that the laws of thermodynamics allow. But we've discovered these two very important forms of energy, because it turns out that what your car does is it takes gasoline, converts the chemical energy into thermal energy, and then converts that thermal energy into work to push your car down the road. So if you drive, you use both of these forms of energy, and they're pretty important to you. So if we think about chemical energy, I mean, how do you quantify it? You're probably used to mgh for potential energy, 1/2 mv squared, and probably even when I wrote 1/2 I omega squared, you were okay with that. But how do we quantify the amount of energy in a gallon of gasoline, for example? How do we do that? Well, we have to measure it, because we want to know how much energy the fuel has before the reaction, and then the carbon dioxide and water have after the reaction. So there's many ways to do this, but the most common is a bomb calorimeter. So if you think of a bomb calorimeter, what is that? Well, it's something where you put a fuel into an oxygen-rich environment, just a little cylinder. You screw a lid on it real tight, and it's like a bomb because it pressurizes, but it does not explode. And what you do is you crank it all down, you ignite the fuel burns completely in the oxygen-rich environment, and you measure how much the temperature change is of a bath of water that this thing is sitting in. You can find plenty of videos online of bomb calorimeters being used to measure, energies of fuels like wood shavings or different species of wood, or even, coal or whatever you have. But when you put the fuel and either air or pure oxygen in, you need to know how much energy those carry in the thermal form, because they're at a temperature above absolute zero. Therefore, they have thermal energy. Thermal energy is just this idea that molecules of gas, for example, are bouncing around, or that solids and liquids move a little bit on the molecular scale, vibrate in particular, because they have thermal energy. They have some motion on the molecular scale. As the temperature of these things goes up, the amount of energy these things have increases. So if you put oxygen in and gasoline, let's say, and you burn it and then allow the combustion products to come back down to 25 degrees Celsius, and of course the reagents or reactants begin at 25 degrees Celsius, then you can figure out how much energy or you can measure how much energy has to be extracted to bring the combustion products down to 25 degrees. Now remember, there's water in this. Remember I talked about your tailpipe and water in the exhaust gases condensing out. Well, if we carefully control the experiment so that none of the water condenses back into the liquid phase, it all remains in the gas phase as essentially steam, then we will measure from the fuel what's called lower heating value, LHV. And in the case of gasoline, every kilogram of gasoline we burn will generate 44,000 kilojoules of thermal energy. Now, on the other hand, if we perform the experiment on the right-hand side, where we make sure that the water all condenses down into liquid and comes out of the gas phase, then we will measure the so-called higher heating value, HHV. So students get confused about this all the time, but all it really is one has water in the liquid phase and the other one has water in the gas phase. And it should make sense to you that the combustion products where we've extracted even more energy so that the water goes from gas to liquid will yield more energy net from the reaction, and in this case 47,300 kilojoules per kilogram. It's not a huge difference, but it's still there, right? It is a difference. So you have to know when you're talking about a fuel whether you intend to refer to the higher heating value or the lower heating value. There is a difference. I like to see things in order to understand them, and so I found this animation and really like it because it illustrates the different forms that thermal energy can take on. You can see the lower molecule slowly translating downward, and you can see its oscillations, right, as it moves. So it has some translational energy and it has some oscillatory energy as well. The upper molecule, on the other hand, is rotating. So it has some rotational energy. It has some vibrational energy. You can see the two spheres, which both represent atoms, pulsating apart. They get closer and then farther apart. And of course, it has translational energy as well. Depending on the molecule, it will have a few different modes that it can oscillate in and or translate and rotate. There's an example of a water molecule on the left that's just sketched, where you can see rotation about 3 separate axes. You can see different types of internal movement or vibration, out of sync, in sync, and sort of a swinging motion. And there are only so many different basic oscillatory motions that a molecule can make. And these can become fairly complex, especially when you have a more complicated molecule. But I wanted to show you a visual representation of what thermal energy is. I mean, you can hold out your hand in the room you're in, and you're probably breathing air, you're going to be dead pretty quick, right? So there's air all around you. That air consists of primarily nitrogen and oxygen, and guess what? Those molecules are not sitting still. Those molecules are diatomic molecules, oxygen bonded to oxygen, for example, that could be rotating. They definitely are translating, and they're probably vibrating as well, as they move around the room. So that's why, if you were to release some smoke in a room, that smoke would dissipate, right? It would diffuse. And the reason for that is because it has thermal energy just as the air around it. So it's mixing naturally with the air around it. You can see this very easily by taking a drop of food coloring and putting it into a clear glass of water. The dye diffuses. Well, how does it move? Well, it's because it's above a temperature of absolute zero, so the dye is going to move some. It's going to vibrate, do a little bit of translation and oscillation. So is the water. So it just naturally mixes and diffuses. Now, a major application of thermodynamics is taking this microscopic energy that we found, this thermal energy, and converting it into a macroscopic form, something we can use, right? So if you think about water in a dam, you might have an idea that, well, if the water is actually moving around, maybe we could just put a paddle wheel in the water, and as the water molecules bounce off the paddles of the wheel, it'll turn the paddle. Well, the problem with that is you're talking about a whole lot of water molecules bouncing off a whole lot of areas of the paddles, and it's just as likely that water molecules will bounce off of one side of the paddle as the other. What's interesting about this, though, is if the paddle's at a different temperature than the water, it will quickly come into equilibrium with the water, because the water will transfer heat to or from the paddle via this microscopic motion. So the microscopic motion is there, it's just that it's not organized into one fashion in order to turn the wheel. We have to somehow organize it, and that's illustrated by making a dam here. It's not exactly how we organize it all the time, but for illustration purposes, this is adequate. We're trying to take this thermal energy, this microscopic energy, and convert it into macroscopic energy, something big enough to push our car down the road or turn the generator at the power plant or whatever the case may be. Temperature units are easy. They work almost like numbers. They're not quite the same, and there's a few confusing details here because the different temperature scales aren't quite like most units. Most units is pretty easy to tell where you have zero of them. For example, length. There's zero length. That's easy, right? Here's some length, here's zero length. No problem. But where is the zero for temperature? For the Celsius scale, the 0 point is at the freezing point of water. But that's not really a true zero. If you take the apparatus shown in the figure here, which consists of a bulb, which has most of the volume of the system, has a pipe so that you can fill the bulb with whatever gas you like, and has a handle off the back so that you don't have to expose your hand to the temperatures you're going to expose the bulb to, and it has a pressure gauge at the top. There's also typically a valve on these where you can fill it with, you first evacuate it, fill it with the gas you want, turn off the valve, and then perform your experiments. Well, what you can do is you can take this bulb and expose it to different temperature environments, maybe coals of a fire or frozen water or whatever you wish to expose it to. And when you do that, you can measure the pressure, the resulting pressure on the gauge. Because if you think about it, as you cool down the gas inside of that bulb, it's going to bounce around slower, right? And so, since pressure gauges rely on the gas basically bouncing off of a sensing surface, if that gas is not moving as fast, it's not going to push the gauge as far. And so the gauge reading, the pressure will go down. Now, if you keep exposing the bulb to lower and lower temperature things, eventually what happens is the gas inside of it will liquefy. Most gas, well, in fact, all gases I know of liquefy at some point. But if we extrapolate the lines on a pressure versus temperature diagram like we see here, the interesting thing is that it doesn't matter what gas you use. You'll see a linear relationship between pressure and temperature, at least for ideal gases, but close enough for real gases. But what's interesting is you could extrapolate those lines and they all go to the same point, negative 273.15 degrees Celsius. So the absolute zero, or the true zero of our temperature range, is below the zero that a lot of scales use, in particular degrees Celsius. Here are some representative temperatures of things. Water boils at 212 degrees Fahrenheit or 100 degrees Celsius. You can make air liquid at negative 312 degrees Fahrenheit. Absolute zero is negative 459 degrees Fahrenheit or negative 273 degrees Celsius. But also we could define a scale which we would call Kelvin, which has a zero at the 0 point, at absolute zero. 0 Kelvin would start there. And then, a nice balmy day of 273 Kelvin is a freezing water day, right? It sounds big. It sounds like a nice warm temperature. 273 sounds kind of hot. But on the Kelvin scale, it's just not, right? That's 0 degrees Celsius or 32 degrees Fahrenheit. They probably need a jacket or a light coat for that. On the other hand, 98.6 degrees Fahrenheit is 37 degrees Celsius or 300 Kelvin. So there's, that as well. That doesn't sound quite right. I think 300 Kelvin's a little lower. I didn't do this conversion. I'm assuming that we can just read straight across. But whatever the case may be, you see that these different scales have different 0 points. The interesting thing is they also have different scale sizes. So if you look at this comparison of Kelvin, Celsius, and Fahrenheit, here they're a little more nicely ordered, and you can see that we go from, let's look at the freezing point of water, 0 Celsius, from 32 to 212 degrees Fahrenheit. Well, that's a change of 180 degrees Fahrenheit, whereas on the Celsius scale, that's only a change of 100. So that means the Fahrenheit scale it has finer divisions, right? There's smaller divisions. It doesn't take as much temperature change to register another degree change. That doesn't mean the degrees Fahrenheit scale is more precise than the degrees Celsius scale, because obviously we're going to get into decimals very quickly, right? And you can just, however many decimals you need, that's what you'll take, and your measurement of temperature depends, or the precision of it depends only on the instrument you're using. But the size, though, of the Kelvin and Celsius scale is the same. The unit size is the same. They have different 0 points, but their unit scale sizes are the same. Some interesting things to note here. The lowest temperature official record was recorded in 1983 in Vostok, Antarctica, and you might say that makes sense given global warming, but actually the highest recorded temperature on record that I know of was in El Azizia, Libya, September 1922. I believe that's still the record last time I looked. So now, that doesn't say that there haven't been points on Earth that were colder than that at some time, or points on Earth that weren't hotter than that, right? These are just official records that apparently have not been broken to this day. I don't think I'd like to be either place and experience either temperature myself. Alright, so conversions. How do we convert between these? Because we can't just treat temperature units like fractions as we do other units. That won't work. If we want to go between degrees Celsius and Kelvin, all we have to do is add 273.15. Now, in this class, that 0.15 is probably not significant. There will be some times when it is, but most time we'll just say add 273 and call it a day. Okay, that's easy enough. So if you have a temperature in degrees Celsius, just add 273 to it, and you will get that same temperature, but in Kelvin. The scale size on the Celsius and Kelvin scale are the same. Freezing point to boiling point is 100 degrees Celsius change, and the change on the Kelvin scale is from 273 to 373. Again, a 100 unit change. On the English scale, you're probably used to degrees Fahrenheit for temperature since we live in the United States. But there is an answer to the Kelvin scale from English units, and it's the Rankine scale. And so we don't say, degrees Kelvin or degrees Rankine. We do say degrees Fahrenheit and degrees Celsius. You'll catch me slipping up every now and then, but I'll try to be good. Rankine is an absolute zero scale like the Kelvin scale. However, it has the same unit size as the Fahrenheit scale. So if we go from the freezing to boiling point of water in the Fahrenheit scale, it'd be from 32 to 212, a change of 180 degrees Fahrenheit. On the Rankine scale, it's from 491 to 703, which again is a 180 Rankine change. So the unit size is exactly the same. The conversion's pretty easy. If you have a temperature in degrees Fahrenheit, add 460 to it, and you've got it in Rankine. Technically, it's 459.67, but we're not worried about that again in this class. We'll round off that 0.67. We'll just round it up and call it 460. Now, here's an illustration of the fact that the unit size is the same in Fahrenheit and Rankine scale, but I've already mentioned this. So if you want to convert a temperature change in Rankine to a temperature change in Fahrenheit, they're already the same. In the same way, a change in degrees Celsius is the same change in Kelvin, right? Because a temperature difference is something different than a temperature. Okay, a temperature is what the temperature is, basically a measure of how much kinetic energy the, say, gas has that you're measuring on the molecular scale. But a temperature change is a difference between two temperatures. And since the scale size of the Fahrenheit and Rankine scale are the same, and the scale size of the Kelvin and Celsius scale are the same, there's no conversion necessary when going between a particular system's absolute and relative temperature units. Their scale size is the same, so a difference in their temperatures is also the same. And I do wish that we were more careful about this. There are many times in this class where you'll have to use an absolute temperature, a relative temperature, or a temperature difference, and you got to know which one of those three goes into the equation. Unfortunately, that's not something that we've really made clear, I think. I think students suffer for that. But here we are. I'm trying to make it clear. Here's the one you're probably used to, probably the one you've been waiting for. How do we go between the Fahrenheit and Celsius scale? Well, you take the temperature in degrees Celsius, you multiply it by 1.8 and add 32. Why? Why do we do all this? Well, look at where the 0 point is. On the Celsius scale, the 0 point, freezing point of water, there it is. On the Fahrenheit scale, that's 32 degrees. So that 32 that we add is an offset thing. It's a bias, right? If you look at this as a y equals mx plus b, well, b is the 32. It's the intercept, right? The 1.8 accounts for the scale size. Remember I said that Celsius have a bigger change than 1 Fahrenheit has. If you go outside and you say, well, the temperature has increased by 1 degree Celsius one day, the next day you go out and you say, well, the temperature has increased by 1 degree Fahrenheit. Which day had the larger change? Well, it's the day with Celsius, right? That's a bigger change in temperature. So you have to multiply the temperature in Celsius by 1.8 to account for that unit size difference, and the 32 is the offset of the 0 between the two scales. Now, that confuses students, because if we want to go between a temperature difference in Fahrenheit and a temperature difference in Celsius, we don't need the 32, because we don't care about that offset anymore. All we care about is the scale difference size. Now, this shouldn't make you concerned, right? This should be easy, because you're used to doing this. If you think about length, an inch and a centimeter are different lengths, right? It takes, 2.54 centimeters to be an inch? that's kind of like saying it takes 1.8, well, you get 1.8 Fahrenheit change for 1 change in degrees Celsius. It's the same sort of thing. So you have to know, again, whether you're talking about a temperature difference or a temperature before you attempt a conversion. Here's a conversion you may not have thought of. How do you go between Rankine and Kelvin? Both are absolute scales, and both actually have the same 0 point, right? They're both tied to 0 at absolute 0 temperature. So in that case, we don't need an offset. Now, I've included it here to make it clear. This plus 0 at the end of the equation is the offset, but really all we need is the scaling factor, the fact that the unit sizes are different between the two scales. The Rankine is simply a finer scale, so you have to multiply the temperature in Kelvin by 1.8 in order to get over to the same point on the Rankine scale. Now, the equation looks exactly the same for temperature differences. It's a different equation because this one naturally does not require an offset. The offset, or the bias between the two in the last example, or the last conversion, was a 0 bias. But here, there's no bias at all. The 0 points don't matter anymore. All that matters is the scale size. And again, the Rankine has a finer scale size, so you've got to multiply the Kelvin scale by 1.8. You've heard of the ideal gas law. Now that we've seen 3 different types of temperature, which one goes into the ideal gas law? Why don't you pause the video and think about it for a minute. Hopefully you've now paused the video and you've unpaused and you know the answer. It's either A, B, or C. I'll give you a hint though, just in case, and then you can pause again if you wish. The pressure has to be an absolute pressure. It has to be the total pressure. Okay, we can't just take what we usually use, which is gauge pressure, which is the pressure above and beyond atmospheric. No, instead, the ideal gas law requires the total pressure for the equation to be true. In the same way, this equation requires the absolute temperature of the gas in order to model the gas's behavior. So the correct answer here is C.